All right, ladies and gentlemen. Today we were looking at chapter 34, and the big idea, what we're really looking at today, is electric current. And so electric current is related to the voltage that produces it and the resistance that opposes it. This is a connection made by something called Ohm's law, which we will look at in section 34.5. Coming up in the second half of the chapter 34 notes. But anyway, voltage produces a flow of charge. And again, this flow of charge, much like the water flowing in a river, we refer to as a current. And that current must flow within a conductor. Current just doesn't flow very well in an insulator. You might get a very, very, very small current, but generally you're going to need a conductor if you want any kind of substantial current to flow. Now, one thing that opposes current is something we call resistance. And resistance is provided by a couple of different factors, which include, what is the wire made out of, how fat around is the wire, and how long is the wire. And then the last thing we're going to look at in this particular chapter is power. But we can transfer energy through what we call power. And power, again, is going to be measured in the units, the same as we saw with power associated with work, which is the watt. And this is, again, how we purchase our electrical power when we are going through and paying our electrical power bill. So 34.1 has to do with the flow of charge. And basically, we're going to see a flow of charge or a current anytime the ends of an electrical conductor are at different potentials than from one end to the other. So how we produce this difference in potential is through a battery or a generator or an alternator. And once those devices are attached to a conducting bit of wire or some sort of conductor, what we will see is a flow of electrons, which we call, again, the current. So heat flows through a conductor. We saw back in chapter 21 or 2, somewhere in there, when there's a temperature difference. And heat is going to flow from the higher temperature to the lower temperature. And when temperature's at equilibrium, the flow of heat stops. Well, this is pretty analogous to what happens in electric current, or the flow of charge, flow of electrons. And so charge flows in a very similar way. Essentially, we have to have a potential difference. Again, something at a higher potential, something at a lower potential. And the difference between these we call the voltage. And so when there is this difference in potential, very similar to a difference in temperature, we will start to see those electrons flow. If there's no potential difference, i.e. we are at thermal equilibrium, we see no flow of the heat, and so we're not going to see the flow of charge if there's no potential difference. And so to attain a sustained flow of charge, we have to keep that potential difference going. If the potential difference stops, it again will stop the flow of electrons. And so one way to think of it, the mouse brings up over here, he says, electrons in a wire are like water in a pipe. You add a little bit of water to the end of the pipe, a little bit of water comes out the other end of the pipe. Well, same kind of thing happens with electrons. You put a few electrons into a wire, a few electrons have to come out the other end. And so, again, here is a couple of little water systems. In A, if we had the water systems, basically what would happen is the pressure caused by the bigger tank over here that's at a higher level would flow over into the lower pressure area until they were at the same level. Once at the same level, there's no more pressure difference to push the water over, and so it would stop. Well, you can fix this by throwing a pump into the system, and that pump would act very much like a battery or a generator, where we can keep those electrons or that water flowing by, again, having the pump bring the water from one end back to the other, just like we can take the electrons from one end and bring it back around. And that's essentially how a system of flowing charge, an electrical circuit works. We're going to talk more about electric circuits in chapter 35, in future videos. But one good way to think about electrical systems is to kind of keep this water scenario in mind. So what happens when the ends of a conductor are at different electrical potentials? You're going to get the flow of charge, which we call current. And so 34.2 is about electric current, and essentially a current carrying wire has a net electric charge of 0. Again, why is this? It is because the electrons that flow in, which would give it a net negative charge, are instantaneously flowing back out. And so as they come in and as they flow out at pretty much exactly the same time, it leaves any particular chunk of wire with a net electric charge of 0 at all times. So electric current is the flow of electric charge. In solid conductors, electrons carry the charge through the circuit because they are free to move throughout the atomic network. Again, we want those conductors to be metal, things like that, which have those nice loose electrons. These nice loose electrons we call conduction electrons. Electrons ultimately, again, are always the things that are moving anytime we have an electric circuit. Protons won't move. Protons are bound very tightly in the atomic nucleus, and because of this, they're locked into position, and they don't have that ability to flow around or move freely. Now, when we have an electrolyte, like the battery acid, the fluid inside of a car battery, we have positive and negative ions. Now, positive and negative ions can flow, as well as electrons inside an electrolytic solution, but you're not going to see the actual proton moving around. It's just a positive ion. Now, to measure current, we look at something called the ampere. And basically, an ampere is the flow of 1 coulomb of charge per second. And so we have to remember back to chapter 32, what is a coulomb? A coulomb is a pretty large number of electrons. It's 6.24 billion electrons, or 6.24 times 10 to the 18th electrons every second. So there's a whole lot of electrons that are flowing there each and every second. And so, again, 1 coulomb, or 6.24 times 10 to the 18th electrons flowing every second would be a current of 1 ampere. Now, net charge of a wire, while the current is flowing, negative electrons swarm through this atomic network of positively charged atomic nuclei. But what we have to remember is that we're flowing in this sort of, they like to call it in chemistry, this sea of electrons that surrounds the nuclei that are found inside of a metallic substance. And this sea of electrons just makes for a very easy transfer of one electron to the next atom, to the next atom, to the next atom, and so on. And so under any ordinary type conditions, the number of electrons in the wire is going to be equal to the number of positive protons that are there. Again, one electron comes out in on one side, it's going to leave on the other side. So if we look at all the sum total of them, the positives equal the negatives. So as those electrons flow, we are going to say that there is a net charge that is about zero all the time. Okay, there might be a small pooling from time to time if there's a problem, but if there are no problems, there shouldn't be any of this pooling. And so what is the net flow of electric charge in a current carrying wire? It's going to be zero. Voltage sources. Where do we get our voltage from? The two most common places are batteries and generators. In your automobile, they, since roughly the mid-60s, don't use generators anymore, but rather they use alternators. An alternator and generator basically work on the same kind of principles. They're just slightly adjusted, slightly different. Alternator just ends up being a little bit more reliable than a generator, and that's why we end up putting it into our automobiles. But these typical voltage sources, again, batteries, generators, are stuff that if we ever were to do a lab, we would want handy in order to get these electrons flowing into a circuit. So charges don't flow unless there's a potential difference. Again, where do we get this potential difference? We have to have a voltage source. And again, batteries and generators are the most common of these devices used to provide a constant flow of electrons. Again, they create this potential difference, which is kind of like tilting a pipe, one end higher than the other. And so when that pipe is tilted, the water would flow down to the lower end of the pipe. Well, a voltage source or a potential difference is created by having one end, the positive end, being higher than the other end, the negative end. And so steady voltage sources include your battery. Again, we use a chemical reaction to release electrical energy in generators. And again, alternators, very similar to a generator in an automobile. We convert some mechanical energy into electrical energy. But the basic idea is both of them create this electrical potential energy, and it's provided at the same amount per charge, so you get a relatively steady amount of potential difference or voltage. And so here we have a battery connected to a light bulb in a very simple circuit. Again, we'll talk more about that in chapter 35. But potential energy per coulomb of charge is going to give us our voltage. Again, the voltage is the difference in what's at one end, the negative end, and what's at the other end, the positive end. And so this provides, again, the pressure to push those electrons around inside of the circuit. Now, power utilities, PG&E, Reading Electric Utility, what they do is they use generators somewhere near your home to provide a constant 120 volts to your home outlet. And then what you have is this potential difference between the two holes in the outlet that averages 120 volts. And so when you put the prongs of the plug in, basically you get this electric pressure of 120 volts that pushes the electrons through the circuit. And this means that 120 joules of energy would be supplied to each coulomb of charge that is made to flow in the circuit. Again, we saw that back in chapter 33, I believe it was. Yeah, 33. So How do we distinguish between current and voltage? There's often some confusion between charge flowing through a circuit and the voltage that is impressed across a circuit. You have to remember, for the physics types, you have the electrons flowing through the wire. And so that is the current that is flowing through. The voltage is impressed across the circuit. This just means that from one end to the other, it's the push from the one end to the other or across the circuit. And so, again, one way to think about it is this idea of a set of some kind of water pipes. But if we have a long pipe that has water, water is going to flow through the pipe if there's a difference in pressure across the pipe or between its two ends. Water flows from high to low pressure. Well, very similarly in a circuit, what we see is that the charges or the current flows through the circuit because of the applied voltage, which is kind of like a pressure, if you want to think of it, across the circuit. So you're never going to say that the voltage flows through the circuit. Voltage doesn't go anywhere. It's just there. It's just a pressure. It's just existing all of the time. It's the charges that move. Again, the voltage causes the current to flow through the circuit. It's, again, that push that makes it go. So what are two voltage sources used to provide the energy that allows charges to move steadily? Again, that's going to be your battery, your generator, your alternator, things like that. All right. Now, there's one other thing that affects the movement of current. It's called resistance. And resistance of a wire depends on something we call conductivity. And conductivity depends on the material used in the wire. Okay, how well does it conduct? It also depends on the thickness of the wire and the length of the wire. And also, we're going to see to a certain extent the temperature of the wire also plays a role. So when wires heat up, they tend to not make the electrons flow as well. You don't get as good a current. But anyway, the amount of charge that flows in a circuit depends on the voltage provided. We already saw that. Again, that voltage source. But the current also depends on the resistance that the conductor offers to the flow of charge. This electric resistance we measure in a unit called the ohm, and it was discovered or largely figured out by this guy named scientist with the last name Ohm. But he did a lot of tests to find out, well, how does one substance pass electricity compared to another? And so again, this is similar to the rate of water flow in a pipe. If you put a bunch of rocks into your pipe, the water's not going to flow as well. It's going to encounter resistance. And so bigger resistance means less current can flow. And so here we look at two spigots coming out of a water tank, a big tank like a big spigot like a big wire will allow a lot of water or current to flow. If you make the wire or spigot smaller, like on the left-hand side of our tank here, you're going to get less water to flow and less current to flow. So big wire, lots of current, small wire, less current. And so again, this analogy that we can compare it to some kind of water system. A valve would be very similar to a switch. A pump would be like a battery. And a line where maybe we are going to feed some water to our plants would provide some resistance. Typically you don't see leakage of current in a system like you might if you're trying to water your plants. But that's kind of the idea. You put a smaller pipe or a smaller hose in this system, and it's going to restrict the flow of water in that particular zone. So resistance of a wire depends on conductivity of the material in the wire. One thing to look at is your periodic table. Some of the best conductors we see are in the column where we see copper, silver, and gold. Well, silver and gold happen to be two of the best conductors around, but they are very valuable substances for other things. So typically, we don't use gold wiring unless it is very, very vital. There was a lot, placed into the space shuttle and things like that where, you could not have problems with your wires or, bad things happen. So why do we use copper in our wire? Well, it's cheap and it does just about as good a job as silver and gold, but not quite. But for the price trade-off, it's better to use the copper than it is to use the gold. But thick wires are going to have less resistance than thin wires. Long wires are going to have more resistance than short wires. So if you ever run very, very long wires in your speaker systems or something like that, you're wiring a speaker system in your house or something like that, you want to use as little wire as you possibly can. Try and not make the runs super long. If you do make them super long, make sure you're using much thicker wires, a larger smaller gauge wire. But anyway, smaller number. But electric resistance also depends on a certain degree to temperature. And for most conductors, anytime we increase temperature, we're also going to increase resistance. Now, there is the property of some materials that when we get very close to 0 Kelvin, we start to see a phenomenon known as superconductivity. And superconductivity would be something that would be absolutely fantastic if we could ever get it to go, to get substances that went at very little or zero resistance when we were at temperatures that are more like room temperature. Right now, superconductivity only happens at around 100 Kelvin. I think the record superconductivity is somewhere around 128 Kelvin. Don't quote me on that one, but that's the number I remember most recently seeing. And so they're always trying to set new records, these guys who are into superconductivity. But they've had a lot of success with some ceramics and things like that. But at some point, if we could ever get it to happen at room temperatures, it would allow our electricity to flow without creating heat. And if it happened without creating heat, we don't have to run all the fans and things like that, which cost so much money to run in our computer systems. Because that's about the biggest cost of running a computer, is having to keep it cool. So we run fans through them all the time. So what factors affect the resistance of a wire? Again, there's temperature, thickness of the wire, type of material used in the wire, and the length that the wire runs. So that's the first half of the 34 notes. We'll get to 34 part 2 shortly.